The Northern Lights is one of the most stunning displays that our planet puts on. One second you're just minding your own business, and the next, the sky's turning pink and green, and there are these lines all over the place, and it's flashing, and it's so good. Despite having lived in Canada my whole life, I never saw the aurora until like a year ago, and over the last year the auroras have become a lot more intense and a lot more frequent as we reach solar maxima. Just a few days before filming this, we had one of the most extreme geomagnetic storms than we've seen in years. The Aurora Borealis is one of the most beautiful things that I've ever seen in my life, second only to your face. Hi, I'm Max. I saw it from across the bar and I like your vibe. I was thinking maybe I can buy you a drink and you can let me mansplain auroras to you for the next 15 to 20 minutes. So even though the aurora is easiest to see at night, it is actually the result of solar activity. So the sun is just sitting out there, minding its own business as it burns itself slowly into oblivion. As it does that, it is sending out massive amounts of plasma, which we refer to as solar wind. The solar plasma, or solar wind, is mainly comprised of protons and electrons, and then there's also like a few sprinklings of heavier elements in there just for flavor. While the solar wind is constantly blowing, it is only during certain solar events that it actually causes auroras. Normally, the solar wind is cruising at a chill 400 kilometers per second. During these solar events, however, it gets accelerated to over 1,000 kilometers per second. The solar events that cause these are coronal mass ejections and solar flares, which are associated with sunspots, and they become more and more frequent over an 11-year cycle called the solar cycle. Right now, we are approaching solar maxima, which is when we're gonna have the highest frequency of solar events going on. A coronal mass ejection is when the sun ejects a bunch of mass from its corona. Go figure. Solar flares, however, is when there's just a flash of light and radiation coming from the sun, and also a bunch of particles. While the precise mechanics behind these phenomena it's a little bit hazy. It's kind of hard to study the sun. Just stare at it for a few seconds and you'll see why. We're pretty sure that CMEs and solar flares are caused by a localized change in the magnetic field on the surface of the sun. To understand this, you can think of it as like trying to force two magnets that are facing the wrong way and you're trying to smush them together. You get to the point where you just can't anymore, and then suddenly one of them flips around. That's essentially what's happening on the surface of the sun. But when the surface of the sun does that sudden flip, it shoots off a whole bunch of material. If the solar material is headed towards Earth, it gets caught in our magnetosphere, and then we get auroras. So Earth has a magnetic field, which we just refer to as the magnetosphere, and the shape of this magnetic field leaves these huge funnels at the poles. And that's why the aurora gets more and more difficult to see the further you are from the magnetic poles. And in case you didn't know, yes, the northern lights also happen in the southern hemisphere. We don't call it Aurora Borealis, we call it Aurora Australis, because it's down under. When the solar wind is moving at its fastest, that means that those particles have a lot more momentum that throws the aurora further away from the poles and closer to the equator. Just for reference, this is what a normal aurora forecast looks like. Not a whole lot going on. And this is what an aurora forecast looks like when we're in a G4 geomagnetic storm. A geomagnetic storm is what we call it when we've got northern lights going on. So as these charged particles are hurtling towards Earth, before they reach the surface, they first hit the atmosphere. Specifically, they hit the ionosphere. The ionosphere is the highest section of the atmosphere, believe it or not, it's made up of ions. Who would have thunk? Sometimes it's good that scientists are really not creative when coming up with names for things. Ions have a different number of protons than electrons, which means that they have a charge, and that makes them super reactive. So when the particles from the solar wind hit the ionosphere, they react with each other and give off light. And that's the light that you're seeing when the auroras are going on. Now, when you're looking at the aurora, it can be kind of difficult to gauge the scale of what you're looking at. So let me give you a hand here. The bottom of the aurora starts about 80 kilometers above the Earth's surface, whereas the top of the aurora is about 320 kilometers above the Earth's surface. Ladies, don't settle for a man who's 6 feet tall. You deserve a man that's 280 kilometers tall.
The ideal male form.
While the aurora can be pretty damn cool to look at, there is a secret danger to these pretty lights. You see, because all these particles that are streaming out of the sun are electrically charged, a moving electric charge creates a magnetic field around it. So with all these charged particles moving through our atmosphere, it actually changes Earth's magnetic field. And if you know anything about electricity stuff, a changing magnetic field induces a current in conductive material, like wires, like transmission wires, like technology in general. Side note here, I find the connection between electricity and magnetism just endlessly fascinating, so I'm probably gonna make a video about it at some point. Sound off in the comments if you wanna watch that, but I'm probably gonna make the video regardless of whether or not you comment, because I already have a script written for it. Please comment anyway. The induced current generally isn't enough to affect like most of our day-to-day electrical stuff. Like your phone's probably not gonna be impacted all that much by the changing magnetic field of the Earth. It's measured in nanoteslas, which is a billionth of a Tesla, just a very tiny piece of a car. Ba-dumts. I think I'm funny, even if you don't. The fact that auroras impact technology leads me to one of the craziest things that has ever happened on our planet, in my opinion. The strongest geomagnetic storm in history, known as the Carrington event. Picture this, the year 1859. The only means of instantaneous long-distance communication is through telegraphs. On the morning of September 1st, two dicks by the name of Richard Carrington and Richard Hodgson both independently observe a solar flare. That night, it hits, sending auroras as far as the equator. It was so bright that it actually woke people up, and people were able to read newspaper by the light made by the auroras. But it gets even wilder. We have the transcript of conversations between telegraph operators from this time, and it's wild. I can't even explain it. I need to reenact it for you. Boston to Portland, please cut off your power source entirely for 15 minutes. Will do so. It is now disconnected. Mine is disconnected and we are working with the auroral current. How do you receive my reading? Better than with our batteries on. Current comes and goes gradually. My current is very strong at times, and we can work better without the batteries, as the aurora seems to neutralize and augment our batteries, alternately making the current too strong at times for our relay magnets. Suppose we work without the batteries while we are affected by this trouble. Very well. Shall I go ahead with business? Yes, go ahead.
This sketch is for aurora education purposes only. Costumes and accents may not be historically accurate.
They kept talking like that for 2 fucking hours, only powered by the aurora. People were getting electric shocks from operating the telegraphs. Wild, crazy, bonkers. Technology really is magic. It really is, if you don't know what the fuck's going on. If something like that were to happen today, it would seriously fuck up our power grid. Widespread blackouts, radio communications shutting down, GPS getting all fuckety. Well, I'm sure it'll be fine. Hope that doesn't happen anytime soon, and we have no way of knowing when a solar storm is gonna happen. So, It'll be fine, right? Also, I recently met somebody who was pretty solidly convinced that the auroras can cause health issues and that like it can give us headaches and make people irritable. There's no evidence of that. The electricity in wires is very different from the electrical way that our body functions. Your body uses sodium and potassium ions, and when an electrical signal is sent through your neurons, it's by swapping those things around. In technology, it's just moving a bunch of electrons through a wire, and all you need to do that is just a magnet. They're very different things. I just needed to get that off my chest because I was unable to correct this person, and something tells me they wouldn't have believed me anyway. They seem to be pretty conspiracy theory brained, so that's lovely. So if you are worried about a sudden widespread shutdown of our modern technological infrastructure, I do have some good news. NOAA, or NOAA, I'm just gonna call it NOAA because that's easier to say. Bars. NOAA has a department that monitors space weather, which is essentially what we call the solar wind. Light moves faster than material, obviously. So the sun being 8 light minutes away means that we will see a solar event happen 8 minutes after it occurs, and then that material still has a long way to travel before it reaches us. Even when the solar wind is traveling at 1,000 kilometers per second, it still takes like 2 days to actually reach us. So we would have a few days notice before something like the Carrington event happened again. So NOAA has a scale for indicating how intense one of these geomagnetic storms is going to be. These storms are ranked from a G1 up to a G5, with G5 being the strongest. And where a storm sits on the G scale is determined by how it ranks on the KP index. The KP index is an average of the fluctuations in Earth's magnetic field taken from various places across the planet. KP of 1 is like nothing really's going on, whereas a KP of 9 is like, holy shit, the Earth's magnetic field is going bonkers. When we see a solar phenomena occur, we're able to make a prediction as to where it's gonna sit on the KP index, and then that tells us what responses we need to do to like mitigate the amount of damage that it could potentially do. So something like the Carrington event probably won't happen for a while. Probably. Hopefully. Maybe. Unless it's something that is stronger than we've ever seen before. In which case we're fucked. Have a great day. Whoops! I totally forgot to mention that all of the information that I used to help me make this video, I got from spaceweather.gov. This website has everything you could ever want. You got this thing here, it shows you what the sun's doing. You got this other thing, which tells you where things sit on the KP index. You got this thing that tells you how many protons are moving around near Earth. You got this other thing talking about X-rays, and I don't understand this bit at all, but it's there and you can look at it and it's damn cool. Most importantly, you got this thing, which is the thing that tells you what the aurora forecast is gonna look like, and that's gonna be the most important thing to decide whether or not you want to stand outside in the cold and look at the sky for a while. Okay, anyway, that's all. Just wanted to share that resource exists, so there'll be a link in the description. Okay, bye-bye! Thanks for watching. If you feel inclined to, make sure to hit that like button and subscribe button, but you know, don't do it because I told you to. Just do it because you want to do it. Okay, that's all. I'm gonna stop recording now. Thanks for watching. Goodbye.